Welcome to my channel, and we have something new here. What we have here? We have here this. This is a transistor buzzer circuit with a power on LED, and every time you push the momentary switch here, buzzer is buzzing, and also the input LED. Just like in the circuit diagram, when you press the button here, current flows into the collector to the base, forward biasing the transistor. When the transistor is forward biased, the buzzer is buzzing because the current now flows directly to the ground through this collector emitter side of the transistor, and the power LED turns on. So this is it, transistor buzzer circuit. This is the circuit diagram. This is my previous project. Now, let us now see the next buzzer circuit. So the problem here, it's not a problem, but you can sound the buzzer, activate the buzzer by pressing the button. Just activate the buzzer by pressing the button. What if you are tired of pressing the button? So I decided to make another module. And this is the previous project I made. This is a buzzer circuit using two buttons. And I'm using a latch switch. This is now my previous project. This is the project, a buzzer with a latch switch. So let us first see the operation of the circuit. When you press the switch, the left side switch, nothing happens. So the right side, so every time you press the switch at the right side, the buzzer is buzzing. While if you want to stop the buzzing, you just hit the switch at the left side. Press the button. And this is my previous project, comparing to the previous one, this one. With this module, I can now control the buzzer using two switches. Start switch and stop switch. But here, that is the difference between the two modules. The first module, the second module. So this is it is an normally open switch or momentary switch. This is with the latch switch. And let us see the circuit diagram of this latch switch transistor buzzer circuit. As you have seen here in the figure, I'm connected the buzzer and the LED to to the output side of the transistor Q1 collector to emitter. This is the output side. This is a bistable mode operation of a multi-vibrator. You see this set and reset, and this is the power LED. Once you press the switch here, current now flows into the base, forward biasing the transistor, and now the current flows here. When I press the switch here, current will flow into this resistor to the base and to the collector. So the switch is off. But when I press the other switch, current now flows into the other transistor, making this to turn on. When this is turned on, this is turned off. When this is turned off, current now flows into the load. This is on, this is off, the transistor, but the output is on. Now, I have also this layout, and also I have also a layout. Where is that? Also a layout for the transistor buzzer. We have a layout here for the transistor buzzer. Now, what seems to be some drawback? I want to have one switch instead of two switches. What if I'm going to use one button? That's what I need. A latching switch that uses only one button. And so I decided to design another module. And this is now also a transistor buzzer circuit. But we are only using one button to turn on and to turn off the buzzer. And this one, I'm using only one push button. Here, I'm using two push buttons. So let us see the operation of this new module. Press the switch. Again, we are now using just one button for the buzzer circuit. Let us see the difference between the two. Using this latch switch, pressing the button, here, and then the previous one. You can design this, depends on your application. If you're going to use just this, or here, or here, it depends. That is now our new module. And if you are interested on this module, how did I design this module? We are now going to see the circuit diagram of this module. This is a latch switch using one button. Comparing to the two buttons, almost they are the same in design. This is some sort of bistable mode of operation of the multi-vibrator. Just like this one. Same, the output to transistor NPN 2N3904. Same. See? I'm now removing this 2 switch into the top. So we have now no switch here. And instead of the 2 switch, I replace it with a capacitor and a resistor connected to the collector side of the first transistor. And I have a switch here connected to the collector and into the base of the first transistor. That is now the difference between the 2 switch using 2 buttons, and this one is using 1 button. Let us first see the current flows in the circuit. This is the initial state of the circuit. Capacitor is charging through VCC, RC1, R1, and to the capacitor. We also have a current flows here to VCC, RC1, RB2, BE to the ground, making this transistor to forward bias. When this is forward bias, makes the current to flow into the RC2, CE, E, ground. So when I use 9-volt supply using the KVL, using 9-volt supply, I got this equation. Voltage at RC1, RB2, 8.35. We have a second KVL here, VCC, RC2, CE. VCC, RC2, CE to the ground. And the voltage drop at RC2 is 8.8 volts. Into the datasheet of the transistor 2N3904, there is some sort of collector current 10 milliampere, base current of 1 milliampere, and the VCE is 0.2 volts. That is the saturation, collector to emitter saturation of this transistor when you are using the datasheet. So it means that when I'm setting the base current IB here, we are going to set a base current of 1 milliampere. According to the datasheet, the collector current now is 10 milliampere if your base current is 1 milliampere according to the datasheet. And the voltage at collector to emitter at saturation, means almost shorted, is 0.2 volts, or it is shorted almost, and actually shorted 0.2 volts. So according to the table, IB, IC 10 milliamps, IB 1 milliamps, and voltage to collector emitter 0.2 volts. Collector current is equal to the current that flows at IRC2, which is equal to 10 milliampere, which is also equal to collector emitter at saturation. What is this? How can you compute this IRC2? Okay. In this datasheet, still there is no collector, or I mean resistor of the collector. There is no collector resistor attached to the transistor. That's why they are using this. IC is equal to 10 milliampere, IB is 1 milliampere. We need to put a resistor here, collector resistor, so that we know now it is now going to use for the load. So without a load, we know according to the table, IC is equal to IRC2 10 milliampere IC sat, because they are in series. Collector emitter at saturation is in series with the IC collector current 10 milliampere without the load, and the collector current of RC2 is 10 milliampere also. They are all in series. That's why it has only 10 milliampere that flows into the RC2. What is now the value of the RC2? Voltage drop, we know that 8.8 volts without a load and with the 9 volt supply, and we know that according to the data sheet 10 milliampere the current flows without a load by putting a resistor here. We get now 0.01 ampere, same as 10 milliampere, and the value of RC2 is 880 ohms without a load. That is now the required value of the resistor without a load. Now, consider now this. If VCC is 12 volts, since we are operating this device with 9 to 12 volts, using 12 volt supply, if you're connecting a power supply of 12 volts, KVL again, the same. Voltage drop, RC2, VCE SAT is equal to, now using the table, 0.2 volts at the VCE at saturation. VCC, voltage drop RC2, voltage drop at CE without a load. So we get now voltage drop of 11.8 volts using a 12 volt supply, while using a 9 volts, 8.8 volts. There is a variation of voltage source or voltage supply we're going to use. Using the Ohm's law, again 11.8 volts, and again without a load, using just the table, setting the base current 1 milliampere and IC 10 milliampere from the table. 10 milliampere now flows into the resistor. What is now the value of the resistor here? 1180 without a load. So let us use 1 kilo ohm. So it means you need to put 1 kilo ohms, or the calculated values for 12 volts is 1180. For 9 volts, it is 880. So in between, we just use 1 kilo ohms. That is now the value of resistor without a load. What is this? VCC, RC1 to R1 to this resistor. Okay, let us now see another current flows here. VCC, RC1, R1, C1. Since the capacitor is charging, okay, there is also a current division here to the RB2 and to the R1. From RC1, current is divided to R1, flowing to the R1 to C1, also to RB2 to the base emitter ground, close to the ground. What happened here is once the capacitor is fully charged, it makes the potential of this node just like the voltage supply. Whatever the potential here is equal to the potential of the source from this node. So it means that VCC is sending a 9 volts here to the resistor R1, this node, making the current to flow to the base emitter. And when this is fully charged, it's just blocking the current flows of the DC current. It will almost open as if there's no capacitor there when it is fully charged. Now what happened here? Let us see. Okay, we have another KVL to the power LED. This is the initial state of the circuit. VCC RD2 D2, VCC RD2 D2, using 9 volt supply, 7 volts. I got 470 ohms. Using Ohm's law, voltage over current rating of the diode here, LED, we got 470 ohms. So we got now the value of RD2 here, 470 ohms, to limit the current flows at the LED. Here we have a value without a load of 1 kilo ohms, but still here we don't have a value yet with the 3 resistor and this RB1 and the capacitor bar. Use figure 4. Okay, this one. This is the situation, the state when I'm now pushing the button. Okay. Capacitor is discharging when pushing the switch, forward biasing the Q1 to trigger pause. Okay. In here, this is on, making the output to turn off. But since this is on, making the transistor to cut off. Current flows to the capacitor and to the base because this one is on and the capacitor is charging. Once you press the button here, as you see in here, the initial state of the circuit, this is on. See the light, this is on, and the capacitor now is charging. Once you press the button here, okay, once you press the button here, now the capacitor, now the current flows into the base CC RC1. You press the button here. This time capacitor is pushing the switch, discharging through R1, that is the arrow, to the node, and to the collector, to the emitter, to the ground. Also, there is a latch here, a latch circuit. Capacitor to the switch since this is pressed, and to the base of the first transistor, making this the forward bias. Because of that, this is now forward bias, makes the current to flow into the BCC RC1 CE ground. Also from the capacitor C1 R1 CE ground. So that is now the flow of current. This is forward bias. Once you press the button, this the charge of the capacitor dumping all its charges to the collector emitter side of this first transistor to the ground, dumping all the charges. So once you press the button here, and because of that, there is also a KVL here. And before that, let us see here. If we use 1 kilo ohms at, okay, this is now the situation. If we use 1 kilo ohms at RC2 with a power supply of 9 volts, this is the former or the previous value of the resistor. Remember, we computed that without a load. 1 kilo ohms without a load. We have a shunt resistor here, or a coupling resistor. If you use 1 kilo ohms, okay, that is the computed value, the previous computed value. Using 9 volt supply, we got see now the operation of the circuit here. Pushing the button makes the current to flow, capacitor to CE, VCC to CE, and then switch to BE, base emitter. Current now flows into the RC2 RB1 to the base emitter, and also current flows into the output when you press the button. That's why there is output or LED turns on, making this transistor to turn off or cut off because current flows into the output and into the base. Because now capacitor is discharging. Also current flows into the power LED. What happened here is, once you press the button and you release it, press the button, release, press the button and you release the button, still there is a current flow because of this latch circuit or this latch line. It supplies a continuous current flow, continuous supply. Even when you press the button here, you release it, there's no more current flows here, but still there is a current flows into the base to the emitter because of this latching effect. This is the continuous supply of current here. There is a continuous supply of current here. there is a continuous supply of current here and making this to turn on. This is turn on, making this to turn off. All the current flows here to the output, to the load, to power LED. Using now the resistor here of 1 kilo ohms, KVL now, RC2, diode 1 to the buzzer. RC2 diode 1 to the buzzer. Transposition. We know the voltage rating of the buzzer, and we got a voltage drop of at the RC2 of 2 volts using 9 volt supply because there is a current flow here. 9 VCC minus the voltage drop, using 1 kilo ohms. Okay, using 1 kilo ohms, you see this? What is now the current flow if you are going to use the computed values without a loop? Using that 1 kilo ohm, we have now here 2 milliampere of current, which is not enough to turn on the buzzer. Or we can turn on this LED, but the light is not good. That is not enough to turn on this circuit, which is not enough to turn on the buzzer using 1 kilo ohms here. So my point here is we need to have the current of 20 milliampere to be supplied to the LED and into the buzzer. That is the current rating of the buzzer itself. If we're using 1 kilo ohms RC2 and the current is now 2 milliampere and resistor 1 kilo ohms 2 milliampere with 2 volts, that is not enough. We need to recompute the current loads using VCC, KVL, RC2, D1, the buzzer. We need to replace the new resistor, so we design a load resistor here or collector resistor based on the load. So this is now the computation. Computed. If current is 20 milliampere, that is the flow of current, you're designing a circuit with the current VCC, RC2, D1 buzzer. Voltage drop at RC2 is 2 volts. Okay, computed already. And now using Ohm's law, since you know 2 volts and the current now for this resistor is 0.02, that is necessary to turn on the LED in the buzzer. We got now RC2 of 100 ohms. We need 100 ohms here for the RC2 to turn on the buzzer. That is down the new computed value of RC2. If 12 volts, using 12 volt supply, since we are using 9 to 12 volts, we got here a voltage drop of 5 volts. 5 volts here. While having a voltage drop of 5 volts here, using Ohm's law. And the current, we need a current of 20 milliampere to turn on these two devices. We got 250 ohms. If we're using 9 volts supply, we are using 100 ohms. If we're using 12 volt supply, 250 ohms. If 9 volts, 100 ohms. And between the two, I'm using 220 volts, 220 ohms available. That is now the value of resistor I'm going to use to turn on this load. So we design now a resistor here, load resistor, that is enough to turn on the load. The new value of R here is 220 ohms. And let us see what happened here. Okay, let's go to another figure. This is again the releasing the button. Okay, when you release the button, as I've said, The current now will still flow into the collector emitter, discharging the capacitor, and this line is still active because of this. Even the latch now, or the line of PK capacitor to the base is no longer exists. There's no more current here. Still the current flows in this direction and into the output. There's a switch situation here. If the voltage drop at 2 volts, RC2 is 2 volts, and the current source is 9 volts. Okay. Using the 9 volts, voltage drop at RB1. Okay, we're now going to compute from this situation or this state. We're going to compute for the value of RB1 using the KBL, VCC minus the voltage drop at RC2, voltage drop at RB1, and voltage drop at the base to emitter. Using that KBL, we got here VCC. If voltage drop is 2 volts and the current source is voltage source is 9 volts, 2 volts. Using this 9 volts minus 2 volts, and the base to emitter saturation 0.65. We got the voltage drop at RB1 6.35 using a 9 volts voltage source. Using the Ohm's law, 6.35 divided by 1 milliampere, which is 0.001 ampere. We got now this 6,330 ohms at VCC 9 volts. I'm setting the base voltage. Remember, I set the base voltage here, IB, equal to 1 milliampere. So we got now RB1 is 6,330. So what if we are using 12 volt supply? 12 volt supply, we get the voltage drop at RC2 of 5 volts. Because 12 minus 5 minus 2 is 5 volts. At the RC2, using that 12 volts, 5.65 base to emitter. We also having a 6.35 voltage drop at RB1, even using at 9 volts or 12 volts, the same voltage drop at RB1. See, using Ohm's law again, the same with the computation of the previous one. Using a 9 volts or 12 volts, the voltage drop at the RC2 is variable. Even the voltage drop at RC2 is variable, and but we are using a resistor of 220 ohms, and there is a constant IB current here, 1 milliampere, and the voltage drop at RB1 is constant also, 6.35 volts. For the value of R1 and C1, choose any value for time constant. That is now the speed. So, what is the value of R1, C1 here? You can compute that using just pick the value for the two. Time constant, that is the speed of the charge and discharge of capacitor. I'm picking the value of 220 kilo ohms and 1 microfarad, making a time constant or discharge and discharge speed of 0.22 seconds. So it's very fast, the charging and discharging of the capacitor. Just pick the values, and then when pressing the button again, it will turn back to initial state. So in here, this is discharging. When I press the button here again, it will now charging the capacitor, and the current that flows into the latch will now flowing into the switch and to the capacitor. When you push the button here, now the capacitor is discharging its charge to the transistor, making this to turn on or turning off, and then current flows into the output and to the base, forward biasing this transistor. When you release the button, it is still latching. After release, pressing the button again, We are now going to press the button again. When we press the button again, now capacitor is now charging and go back to its original state, a stable state, which is capacitor is charging, and the latches will remove the current flows directly to the ground. That is the operation of the circuit. And when pressing the button again, it will turn back to initial state. RIB1 flows into the capacitor to the ground, disconnecting the latch. So we have now this. This is the latch switch 1-button circuit diagram, and these are the actual values: 470, 220, 6K, 6K, 220, 220, and this is my schematic diagram, and this is my layout, and